Okay, let's go ahead.
Okay, so thank you very much for the invitation. So the talk today is about the TPC. It's called Triangulated Persistence Category. It's based on the joint work with Biran and Octav Cornea. So we have been playing with this for the past 1 or 2 years. So a TPC, roughly speaking, will be a combination of 2 structures. One structure is a triangulated structure, and the other structure is a persistent module structure. So I believe the first one is well known for everyone. Like you can talk about the exact triangles in this structure. So the second one, the persistent module structure, I'm not sure if everyone knows this. And I can see some people from the audience probably know this, but if not, let's. I want to take a short detour to the to find the file. So I will discuss a little bit about this. Okay, a little bit about this persistent module. It takes probably 15 minutes. So the persistent module structure often appears in some subject called topological data analysis. You will often see this TDA, and also applied to algebra topology or computational topology. And one of the earliest paper about persistent module is from Zamorodi and Carlson. It's called Computing Persistent Homology in 2005. It's been a while. And Carlson is widely regarded as a founding father of this theory. So the definition of persistent module is easy. So here is the definition. It consists of the following data. So we'll have a R parameterized. Well, you can take whatever poset you want, but usually let's take R. The R parameterized family of K modules, vector space, and for 2 parameters s smaller than t, you have a map. It's called persistent structure map from the Vs to Vt, and satisfy the following 2 properties. So the first property is if t is the same, if s is equal to t, then you have identity map on this vector space. And if you have 3 parameters, r smaller than s smaller than t, then you have this functorial properties. R goes to S, composite S goes to T is the same as R goes to T. Okay, so, and sometimes people will put some further condition, like if you want to apply this to geometry or topology, you sometimes put like when T is sufficiently small, you will get 0, or when T is sufficiently larger, you will be stable, like there's no, all the structure maps will be just isomorphisms. But here, let's take the most brief definition. And I think if you see that, if you see this definition, everyone will talk about this from some example, and this example is called filter Morse theory. So here is an S2 on the left of this window is S2, and you have 4 correct points, P minimum, P maximum, and your Q1, Q2. And in particular, Q2 has index 1. And you have a height function from this S2 to a real line. And so you can talk about what's the height of all the correct points. So for the classic Morse theory, as you probably all know this, you first formulate a vector space. It's generated by 4 correct points. Here are the 4 correct points you can see from a picture. And you will formulate a boundary operator, a Morse boundary operator, and counting the gradient flow lines. Like for example, Q2 goes to P minimum twice, front and back. And then you show that this boundary operator is a boundary operator, square is equal to 0, and they formulate the homology theory. And the Morse theory basically tells you that the homology from this computation can recover the singular or classical homology of a manifold self. Okay, so this is for classic Morse theory. How about the filter Morse theory? I see that you are not going to compute the entire homology. Sorry, you're not going to compute the homology of the entire manifold or the entire chain complex. You're going to compute the homology of the chain complex with generator smaller than whatever the given height that you have. So if the height is very small, there will be no generator appears. So the chain complex just 0. If the height is just between the P minimum and the Q2 here, somewhere here, they only have 1 correct point, just P minimum. And you keep computing this homology in this way. Then you will have for each of this parameter T that you specify, the height you specify, you're going to have a homology, and you define this homology as a t parameterized. I mean, the vector space at time t, or at filtration t. And here you actually have a structure map from S to T, S smaller than T. This was induced by the inclusion. You have the inclusion of chain complex that is commutes with boundary operator, then you pass to the homology, and you get this S and T. And you can check, it's a good exercise or example, check that the if I do this, if I assemble all the data in this way, you will find you will get a persistence module. This is a very classic way to get a persistent module from geometry. And then you might wonder that what's the benefit to have this filtered version instead of the classic ones, right? The filtered version actually can provide more information in the following sense, right? So when you keep changing the filtration, you keep computing homology. Because obviously when the T is sufficiently large, right, you will recover the classic Morse theorem. But you notice that there's something you probably will not see from the classic Morse theory. Like this Q2 has index 1, but the Morse theory tells you that the homology, the resulting homology must be equal to S2. So this index 1 will not see from the classic one, but you will see it from the filter one, right? Because when you somehow, like when you go to Q2, you will have only Q2, and there's nothing Q2. Q2 is there, right? And until at some moment, you'll notice that Q1 plus P max over 2 will Q2. So this means that you will have Q2 was born at some certain level. It will last for or it persists for a certain amount of time until it hits another correct point that kills it. Right? This actually gives you something that you will not see from the classic homology. And this is basically called the homological non-essential generator. And all the things you can see from the classic homology or Morse theory is a homological essential generator. So this is basically the one of the benefits you can have from this filtered version of Morse theory. Right, as I write here, Q2 is born at a certain level, killed by something when you filtration high enough, when you see both Q1 and P max. And in particular, Q2, you will not see that Q2 in classic Morse theory. And this thing can be actually formulated in a quite algebraic way. So here's two main theorems in this story. So the first theorem is called Decomposition Theorem. And so any persistent module admit a unique decomposition. I write in the following way. Right? V is a persistent module and decompose a direct sum of Ki. By the way, K here is in the notes is some field. And I is a certain interval. Like here I write interval AB. You will see some like a strange notation. Left closed, right open. Sometimes people use left open, right closed, and sometimes it depends on convention and also a specific situation that you want to apply. And this KAB is called interval type persistence module. It's particularly easy. Right? Yeah, here's R and here's interval AB. And KAB basically can view this as a trivial vector bundle dimension 1 over this interval AB. So over each point of in the AB, you will have like one-dimensional vector space K, and the structure map here just identity map from K to K. And if one of them is outside A and B, just the structure map is always just 0. Okay, and remarkably, every persistent module can be decomposed in this way, and it's unique up to the permutation of this interval. And because of this uniqueness of, you can talk about you can extract only the interval from this decomposition, AB. And this is called barcode of B. Right? If you assemble everything here, it's like something sometimes is bigger, sometimes it's shorter. And the important thing here is that if you are looking at some homological essential generator, this will correspond to a bar such that B is infinity because this guy was born at some time but never killed. Right? You will eventually see in the classic homology. So B just infinity. And sometimes if there's new information appears, if like here, if something was born at some level and killed at some other level finite time, right? You will see some finiteness bar. Actually, finiteness bar is the new information that provided by this filtered version. Okay, and here is a small exercise. You can work out the barcode of the persistence module from the Morse theory above, right? Here is a very concrete example, and you can arbitrarily associate some height of the query points, and you work out what is the barcode of this persistence module if we assembled in this way. Right? It is a good exercise. Okay, and then another theorem tells you that how to compare two persistence modules. It's actually not appeared very much in this talk, so I will very briefly talk about that. Here is called the isometric theorem. So on the left-hand side, if I give you two persistence modules, you have U and V. Then there is something called interleaving distance. It's quite defining a quite geometric. Yeah, okay, so I'm a bit cheating. Right? It's still algebra, but is compared with right-hand side, it's more geometric. And the right-hand side, once you pass from the persistence module to its barcode, just collection of intervals, right? There's also a distance. It's called the bottleneck distance. It's a very strange name between the two collection of intervals. And the definition of this, the right-hand side, is very combinatorial. So the good thing of that is the left-hand side is sometimes can be defined in a very nice way, but very hard to compute. Look, I think it's fair to say it's very hard to compute. But the right-hand side is very combinatorial, so it's relatively easy to compute. And if I cannot do this, I can put it into computer, and somehow a computer can help me do this. And so this sort of transfer from the non-computable to computable. So this is a good thing. And for the left-hand side, what do you mean by interleaving? Right? Sometimes you have, for example, you have interval type persistence module 0, 5. You can build it just interval 0, 5. And the right-hand side has something that seems very close to it, right? Like the 1, 6 is just a shift of that 0, 5 by 1. And here is a shift on this is the shift on right, the shift on left. This is some expanding of both left-hand side, left endpoint, and right endpoint by 1. This is a shrink, the left endpoint, right point also by 1. And they all just one interleave, right? You can just basically regard this as two, at least in this case, two intervals are almost the same, except you can adjust the left-hand side by 1. So this is called one interleave. And the rigorous definition is can be derived in somehow in this way. And the right-hand side bottleneck distance is a little bit more complicated. Since it's not in the focus of this talk, I will not give the definition. And if you're interested, you can check any book or any paper about this. One thing that I want to emphasize is once you have persistence module, right? The natural morphism between persistence module is called persistence morphism. Obviously, it will be a R parameterized family of morphism. So for you have Ft for T in R, and for any T will be just the map from the T piece of U to the T piece of V. So that, and obviously it must satisfy some compatibility with the persistent structure map. And if you go from US to UT by the U persistent structure map, and it must become and go from UT to VT by FT. It must commute with you go first by F and then go by the persistent structure map. Okay, because of this commutativity, you notice that sometimes there will be no non-zero persistent morphism between two persistent modules. And here is a very typical example. Again, let's take 0, 5 and take 0, 6, and claim that there will be no. The only persistent morphism is 0. Why? Because if you have that, if you have some non-zero things, then you must go this way first, go here, right? But right. So this is non-zero, and here is isomorphism by definition of the interval type persistent module. Here the same thing, you have to go something, but unfortunately we go outside this interval 0, 5, so it might be 0. And here go down is 0. So you have something 0 is equal to something non-zero. So this is a contradiction. So this tells you that you have, when you play with two persistent modules and the persistent morphism between them, you have to be very careful. Sometimes just equal to 0. Okay, and finally, let me just say the remark that persistence module right now has many applications because many algebraic structure or homology theory has been updated or upgraded to a filtered version. Now, this talk today, this TPC, it will be an example of how you upgrade the triangulated structure into a filtered version. And so here the persistent module has important applications in geometry and topology. And my research background is in symplectic geometry, especially in Fur theory. And if you don't know Fur theory is a filtered homology theory on the loop space, deal with loops. And the original of that is to try to solve some dynamic problems. So because it's a filtered homology theory, right? So it's very natural to upgrade the Fur theory into a filtered ones. And that's the reason why the persistent module start to play some role in symplectic geometry. So let me show this one. Here's a book. It's called Topological Persistence in Geometry and Topology. This is a book I wrote with a few people, and these sort of summarize the application of persistent module in I think well in geometry and topology, and also sounds a little bit in analysis. Okay, if you are interested about the stuff that I talk about only for the persistent module, you can just go through, just check the book. Okay, so that's all I want to say about the persistent module. It's a very brief. And now once we have that, now you know what's a triangulated structure, you know what's a persistent module structure. Now let's move on, right? So first remark is there are two structures. What we talk about is called triangulated persistence category. There's something else that you can try to do. It's called persistence triangulated category. Is that the structure is switched by definition, right? What is the persistence module, right? It's a family of modules. What is the persistence of triangulated category? Be a family of triangulated category with some structure maps. And this is not what we are doing. We did not create a family of triangulated category, but we attempt to do that at the beginning of our project. We failed. We do not know how to do that. So we sort of switch the structure. So we get something like a triangulated persistence category. So in general, these two things are not the same. And still, for us, this PTC is still mysterious. Okay, so the outline of the rest of talk is I will start to tell you something about before TPC. It will be something called a PC, persistence category. And usually it's different from the classic category you've seen. It's a very known ability. And once you have persistent category, a special case of a persistent category is TPC, triangulated persistence category. And I probably don't have much time to talk about that, but there's many examples, supporting examples of TPC for example, from symplectic geometry. And then I will talk a little bit about what's the K group of TPC, because it is a middle triangulated structure. So it's natural to talk about what's a K group. And from the K group, the new thing is that you can extract some numerical data, a numerical invariant from this K group, better than the classic K group. And then those numerical invariants will be helpful to apply in symplectic geometry. Okay. Yeah, still I'm not sure if you have time to talk about the application, but let's see the K group is usually called K0 group, and you can also talk about K1 group, but it might be hard to do that. So the K group, don't worry much. The K group is the classic K group that you know from textbook, and it's a K group of a part of TPC. And we do not study something called a persistence K group. We do not study a family of K groups. That's also something interesting that you can try to do, but we don't know how to do that. And here you might wonder that if I extract numerical invariant from the story, that do I need the entire TPC, the entire structure? And the answer is yes. We need the entire TPC to extract the numerical invariant. If you only consider part of that, then some of the application just fails. Okay, so that's enough about the outline. Let's see what's the definition. So I will go directly to the second page. I'm sorry that I transferred this from the OneNote. When you know that when I transfer the PDF file from OneNote, the page breaks. There's some overlap here. Let's start from here. Okay, so a persistence category, C, is a category such as for every two objects X and Y in this C, the morphism set is a persistence module. Well, this is exactly the definition that I gave, though I just try to tell you what the persistence module is. R parameterized family of vector space, finite dimensional vector space, and you have the structure map from R small when R is smaller than S. And here is a category, so we have a composition. Right? The composition must be compatible with the filtration. You have filtration S, filtration R. So composition basically goes to filtration R process. There's another option that you can do. Instead of plus, you can take max of R and S. That's actually we have some so it's sort of more restrictive than this R process. We have some theory about that, but we actually don't know what's the right application. It seems like all the geometry that for us is always goes to R process. And there's a compatibility, right? The composition must be compatible with the persistent structure map. So you have a persistent structure map on the left-hand side for each of the factors. And then when you first do this the structure map, then you go composition, must be the same as you do composition first, and then you go to the structure map. Okay, so that's the definition of persistent category. This is a very natural definition. For example, if your object is only 1 point, then this category is a persistence algebra. Is better than persistent module because you can multiply two things, and all the persistence module together will form a persistence category. This is a quite big category. I denote this as a PER. So let's see how does the morphism looks like. So the morphism in this big category between two persistent modules. Here the persistent module is let's take some example, easy example, the interval type persistent module. And how do you construct the morphism? The morphism must be also a persistent module, right? So in order to do that, I'm going to consider the persistence map or persistent morphism from one to the other one. This notation means that I reparameterize the parameter of this persistent module by shift by R. Okay, and I for each shift of R, I'm going to consider the persistent morphism between these two guys, and you can naturally have this persistent structure map, and this is basically assembled together what become a persistent module. Okay, so the example is the following, and here comes something is interesting. As I mentioned earlier, sometimes when you deal with two persistent modules, the only persistent morphism here you consider is 0. And here is some example here, right? You have 0, 1, have 0, 2. If there's no shift here, just 0, 1, 0, 2. And there's only persistent map is 0. And you start to shift a little bit. Let's see you shift with negative. So here, by convention, if you shift by negative, the corresponding barcode shift right. So here, and still, this is the only persistent morphism is 0. And you still have this phenomenon that goes here 0, down here is non-zero here. But you shift on the left, now you notice that you actually start to get some non-trivial persistent morphism. But you cannot shift too much, because if you shift too much, then these two support will be destroyed. And again, the only persistent morphism will be equal to 0. So there's only very narrow room that you can shift to guarantee that you will not have any you will have non-trivial persistent morphism. And in fact, you can check that as a persistence module, the morphism between these two persistence module is another interval type persistence module, which is 1, 2. Okay, you see that you can shift to 1, somehow keep shifting until from 1 and until 2, you are not going to shift, otherwise the support will be destroyed. Okay, if you are not familiar with this kind of language, right, there's a different language in terms of sheaves. If I consider the sheaf, a constant sheaf is over 0, 1, another constant sheaf over 0, 2, you consider sheaf home from between these two sheaves. And it turns out if you compute that, you will get another sheaf, constant sheaf over 1, 2. That's precisely this corresponding to the interval here. And in general, you have actually a formula from A, B, C, D. You will have this formula here. I think for people who do a persistent module, from the shift perspective, this formula is very well known. Okay, and you can see that from this perspective, the persistent module in some way is related with shifts, right? And indeed, and there's a group of people actually did some very good job in how to translate between the persistent module and shifts. Now, once you have a persistent category, when you have two persistent categories, then the natural way to connect them is by functors. You have something called persistence functor, f from C to D. Okay, the way to define that is there's no mystery to define. Very similar to the classic. The only difference is that now we have filtrations. We have R here, so you have to take care of what's the filtration change. Here we take the convention that you can take different convention. This is the convention that we take. The persistent functor will not change the filtration. So the filtration R, when you map here as a functor, well, goes to the filtration R. Okay, this is the only thing that I want to emphasize. Now, if you have two persistent functors, f and g, and we connect them is by the natural transformation. Now here it's called persistence natural transformation. And again, it's very similar to the one that's in classic way how we define it. You have an evaluated some object, you have some diagram, right? And now the thing here is you have to again relate it with how the filtration change. Now this time, I have to say that the natural transformation will have some filtration associated to that. And here for any object X, the morphism when you evaluate some object will be a morphism but with a filtration R, and this R is independent of X. This is uniform for any X. This morphism with R with morphism with filtration R of Fx and Gx, and this R is called the shift of this persistent natural transformation. So again, the persistent function will not have any shift, and nothing to do with the filtration, but the natural transformation will have a certain weight, the shift. Okay. Now here comes a good example. It's actually an example that will play a lot in our story of TPC. And here is an example of family of persistent functors. It's called the shift functor. It's parameterized by R. So each of the sigma R is a persistence functor on C. And I have to see that this is not a data from the persistence category. If I give you a persistence category, it does not naturally admit a shift functor. You have to specify what the shift functor is. Maybe at some persistence category, it does not admit any shift functor. But luckily, in most of the application that we have, the shift functor is very natural. Now, here is a family of persistent functors. It satisfies the following two properties. The first property is additive. You have a shift functor sigma s with filtration s, and composed with the shift functor with the filtration r. Then it will be the same as sigma with r plus s. And again, there's another theory that you replace r plus s by max of r s. And when this R is 0, you have just the identity map. And how to talk about this? What's the relation of the sigma R and sigma S? We have a natural transformation, persistent natural transformation called sigma RS from sigma R to sigma S is a natural transformation. But again, recall that natural transformation, persistent natural transformation must have a filtration. And this here we define the filtration as S minus R. Okay, so in particular, if I evaluate some x, right? If I have a sigma r, x goes to x, this is given by this natural transformation r0, because sigma 0 is identity. Evaluate at x. What's the filtration of this guy? Right? The filtration of this guy is s minus r, so it's 0 minus r is minus r. And let's say r is positive. And every filtration below 0 is something that we don't like. But it's okay if we don't like the filtration below 0, we can use the structure map to boost things up to filtration exactly as 0. So we will have the map theta r0 with filtration minus r, and then we boost everything up by the persistent structure map. Eventually, we're going to have a map from sigma Rx to X, but with a filtration exactly equal to 0. And this map is very important. I will denote this map by eta Rx. A good exercise is to figure out, we have this big category which consists of all the persistent modules, right? And I have already tell you what is the home of this guy looks like, at least in this example. So try to work out what is the what is the shift function. Here I actually tell you that there exists a shift function, and what is the natural transformation between sigma R and sigma S, and what is this eta XR. And you will work this out, you will notice that it will be very familiar with some of the classic notation in the classic, not classic, standard persistent module theory. Okay, so once I introduce this notation from the map sigma Rx to X, I call this R acyclic if this map is 0. And this can be viewed as some quantitative version of an object is 0 in a classic category. Now, what is object is 0 in the classic category? The identity map is 0. Right? Here, it's not identity map. It's almost like an identity map up to a shift sigma R. So we call this R acyclic if this map is 0. And this R acyclic actually is an abstract formulation of many things in persistent module theory or in classic theory. For example, in Morse theory, we have seen that you will see some homological non-essential geometry, but you won't see, you will be killed in the middle when you move from filtration minus infinity to infinity. And you will see that this homological non-essential ones can be formulated as a certain R acyclic things. And you have a barcode, right? In the barcode, sometimes you have infinite length bar, sometimes you have finite length bar. And I mentioned earlier that finite length bar corresponds to something born at some time and killed at some time. And those things is also called R acyclic, or is related to R acyclic. And some story, a shift story in symplectic geometry, there's a Tomakin's category, and there's some element called R torsion element, which is also a version of R acyclic. So this formulation, I think, is a very it's a good formulation. It covers a lot of special cases. Okay, so that's all I want to say about persistence category. It's I probably stop here for 1 minute or 10 seconds if you have any questions. Okay, so you have no question. Let's move to TPC, and the one that the focus of our talk. So TPC will be a triple. It will be C, which is a persistence category. We have discussed for the past 20 minutes. And there's a T. It's called the translation autoequivalence. And the sigma is the shift function that we just talked about here. So you see that we have to specify what sigma is. Now a TPC will be, sorry, this is a broken page. So, okay, so TPC will be a triple here, such that we satisfy the following axioms. So there is a category called C0. So if you feel like the morphism set is too big, right? It's the entire persistent module is too much information. You can focus only on the level 0, only 0 piece, right? And this also become a category. It's actually become a Billian category. Now I see that this category is one of the axioms is that this category is triangulated with a translation autoequivalence T. And this is where the T comes from, it's associated to this C0 category. And this T commutes with the shift function sigma R. So sometimes you need to switch these two things. I want to shift first and transit, or transit shift. And this tells you that there's no difference here. And now the third one is the most important one. Okay, so it's the most important in this talk. So recall that we have this very special map. It goes from sigma Rx to X with filtration precisely equal 0 because we're boosted up by the persistent structure map. And we see that this map can be completed into an exact triangle in C0. And here this Q will be the cone part that you put here. and this Q must be R acyclic. So you will have an exact triangle in this way, in this form, in C0. And this is a quantitative analog to the classic axiom in triangulated structure that you have identity map can complete into an exact triangle, which put 0 here. And here there's no identity map, something similar to identity map with some shift. And I will put and 0 here. It will be something similar to Q, which is R acyclic. Okay, this is how you sort of put this quantitative taste in the classic triangulated structure. There's a few more axioms, but I will not list here. Okay. Now here's some example. I think this example will be important in the later part of this talk. If I give you a TPC, you will consider a subcategory consists of a cyclic object. So again, what's acyclic means? Is acyclic means that you have this almost identity map is equal to 0. And this also will formulate the TPC, satisfy all the properties here. And it's sometimes denoted by AC, acyclic persistence category. Okay, there's a lot of definition here, but let me tell you that what's the motivation. Then our motivation is actually very strongly from the symplectic geometry. There's a story called Lagrange cobordisms in symplectic geometry that you can sort of decompose stuff, and eventually will formulate everything into a category. And in symplectic geometry, as I mentioned, there's very often there's some natural filtration appears. So instead of formulate a triangulated category, there's actually put filtration inside. That's why we have this TPC. The upshot of this TPC of all the story here is that we can define some pseudometric and call it algebraic fragmentation pseudometric on the object set. So you give you two objects in this TPC, you can talk about what's the distance of the two objects. And the way to do that is to do some fragmentation. I'm not sure if everyone knows what a fragmentation means. So here I put a remark. The fragmentation sometimes means a cone length in algebra topology. That if I give you two things, how many cones you're going to have to decompose one thing into the other thing? Decompose as cones. You have a lot of exact triangles, and here is the same thing. It's called fragmentation. Break everything into small cones. Right. So there's a recent story by Biran, Cornea, and Shlukin. They have some concrete construction in a concrete setup. But here, this theorem is can be read as an abstract formulation of their story. Okay, and I cannot, of course, I don't have much time to talk about how to prove the theorem. But one of the key steps is actually in the construction from the TPC that you can get is to define some a weight of the triangle, or more precisely, you're gonna see some new family of exact triangles. It's called the weight R triangle. So those will be included into the set of exact triangles. It will look like this. If you have x goes from x to y goes to z, but once you have reached back to x and up to some shift t, you're gonna shift this by minus r, sigma minus r. And we call this a weight R triangle. And once I mentioned here, like, what's a cone length, right? You're going to have a lot of triangles to assemble things together to move from one object to the other object. But if we use the weight R triangle, you're going to have a lot of weighted triangle. You go from one object to the other object. Then the weight will be just all the distance between these two things will be the smallest the weight, sum them up. Then you can reach from one to the other one. Yeah, this is basically how you define the distance. Right? You first define a family of weighted triangles. Use these weighted triangles to formulate a lot of cones. And for each of these, you're gonna have some weight, and you sum up all the weights together, and you minimize all the possible weights. You will have the difference, the distance between one object to the other one. And this is actually very important stuff in I'm not expert of algebra. I'm not sure if this has been appears in some formulation in algebra in history, but at least in the symplectic geometry, this is something new.
June, there's a question in the chat. Have you answered that already?
Oh,
sorry, I just
no.
noticed.
So the question is, do we need to fix R in the definition of a sigma? And the answer is no. You're going to consider all the possible R. Okay. That's another question. Okay. So right. So there's a slight few things I want to say about this weighted triangle. Now, this weighted triangle is this not much new. We put here, just put the filtration. But it turns out it has a lot of very nice carry from this definition. And the one way you can view this weighted triangle is to think about that this is an R interleaved in some way from a true exact triangle with C0. True exact triangle does not have any shift here. Right. Now here is R interleaved will be very misleading because there's at least 4 things here. So what do you mean by R interleaved? There will be ideally it will be R interleaved of all the you have X to something X prime is R interleaved here. You have Y to Y prime R interleaved here. There's something interleaved here, something interleaved here. Right? You can do all the interleaving of the spot here, but unfortunately this is not good, because if we do that, then R here, we have something accumulated in this cone part. So this definition we have here will be only R interleaved at the cone spot. But it will be very challenging to see what's the right way to define an R interleaved relation of triangles. I think because you have to somehow find the. Okay, so this just for those people who actually know the story. If you to define the R interleaved for triangle, you have to count what's the how much weight of the homotopy here. The weight of the homotopy, how much you're gonna have a homotopy here will be added up in the cone. So you will not have a nice R. You have some R plus something and R. So this will be you can do that, but it looks like the algebra looks quite complicated. Okay, so to move on, especially to move on to the K group, I want to say another thing that is probably known to people. It's called filter chain complex. It's actually easier. So persistent module looks a little bit like new to some people. Right? But if I tell you working on the chain complex, it will be nice if I actually tell you that you work on the chain complex with a filtration, and this filtration looks like a height function. You can just exactly view this as a height function valuation. If I give you generators in here for this complex, how big the height is. The classic thing is the one that you have just seen. You have a Morse complex with critical points, then the height function tells you that the height function just precisely this valuation. Okay, the only thing you need to put on the height function is that height function will not increase the the boundary operator will not increase the height. This is the only condition we have. Okay, so if you put this extra ingredient, then you're gonna have you're gonna have something called filter chain complex. And it's called the category of that is called FCH over field K. And there is a theorem that was, I think it was first recovered by Brownikov in 1994, but in 2016, Mike and I sort of rediscovered that and making more clean or stronger. It says the following thing, and after filter homotopy equivalence, every filter chain complex will be decomposed into the sum of the following 2 types of chain complex, still filter chain complex. This is multiple filter chain complex. This first type is a chain complex which only one generator and the rest of them just 0. And the AK corresponds to the height of the filtration of this generator X. This is the first type, E1. And you have a second type, E2. And E2 corresponds to a chain complex with 2 non-trivial generators. Y goes to X, and the rest of them equals 0. And the 2 parameter here is correspond to the height of the X and Y. So X has BK and the Y has SIC. And clearly, right, you will see that this E1 corresponding to a bar because the generator appears and never killed. So it corresponds to bar AK and to infinity. And this type 2 filter chain complex corresponds to finite length bar, BK and SIC. Okay, and the theorem is following, right? The theorem that every filter chain complex is composed in the following way, right? So eventually it also arrives at the barcode. So somehow like the filter chain complex, the category of that is somehow equivalent to the category of persistent modules. And there's a proposition that you can view this filter chain complex as a DG category or filtered DG category if you put the filtration inside. Then the homotopy category of this, the filtered DG category, which is H0, counting degree 0, homology, is you can check is a TPC, right? So the filtration, so the triangulated structure comes from the classic proof that the homotopy category of filter chain complex, category of filter chain complex is a triangulated category. And this persistence structure comes from its filtration. That's how these two things combined together. This is actually a very universal object. You will see that in a minute. It's actually related with the K group. I think I have just a few minutes left. So let's quickly go through the K group. So I believe everyone knows what K group is. So for a TPC, let's see what's the K group of TPC. So recall that the C0, right? You only count the filtration 0 morphism. Is triangulated. This is by definition. And I can consider the K group of just C0. This by definition is a abelian group generated by the object or isomorphism class of the object. Module the relation that if you have, sorry, it's broken. If you have some exact triangle X goes to Y goes to Z and it's an exact triangle in C. This is a classic definition, but only apply on C0. Okay. And similarly, you can construct that acyclic ones. The acyclic category is also acyclic object also form a TPC. You can talk about the 0 category of that and consider the K group of that. Okay, here comes another theorem that we worked out recently. So if we consider the previous one, the homotopy category of the category of filter chain complex, then we can compute very precisely what is the K group of this category, or the C0 of this category. So let's say I want to write things in a clean way. So let's say that here I have a strong condition is that every chain complex in total finite in general. So this index is finite supported. And then we will have a ring isomorphism of the K group of C0 to the lambda P. P stands for polynomial. And another one, if I consider acyclic ones, it will be a subring of P. So actually, it's not even a subset of lambda P. So what is lambda P? Right? Lambda P is not mysterious. Lambda P is called canonical polynomial ring. It will be like a polynomial, but over a coefficient Z. The only thing is like the power here is in R. It's not in integer. This is very natural in symplectic geometry. So sometimes we have the filtration put on the top of the T. The filtration is taken in the value in R. Okay, so here's a theorem that says that the K group is isomorphic to the canonical polynomial ring, and here's a similar thing to the acyclic ones. And to prove that, it will take a few pages, actually more than a few pages to prove that. But I can tell you what is correspondence to save time. So here on the left-hand side, it's a K group. On the right-hand side, it's not polynomial ring, canonical polynomial. So recall that E1 is this type 1 chain complex, right? One generator with filtration A, and it never die. So it corresponds to bar A infinity. So E1 corresponds to the monomial T to the A power. And similarly, E2 corresponding to T to the B minus T to the C. But T, there's B here and T is C here. So T to the B minus T to the C. In general, right, by the theorem, Biran-Koff theorem, or the theorem that I did with Mike Usher, each one of the filter chain complex it decomposes a direct sum of that. So you will have some things together will have some polynomial like this. And also the for the chain complex, you can consider the tensor product, and the tensor product corresponding to a product in the K group, and this precisely corresponds to a product in the polynomial t to the a times t to the b, t to the a plus b. And there's something even more complicated, right? Here is a product of E1 type. You can consider product of E2 type. For this one, you see that on the right-hand side, you will have when translate from E2 type to polynomial, it will be t to the a minus t to the b, and times t to the c minus t to the d, you get some formula like this. It's easy. But on the left-hand side, there's how to do the tensor product on the chain complex. Right? You will do something. You have to do some work, right? What is generator? What's the degree? And you will have this famous formula right here. I think people do persistent module know this formula well. And when you pass to the K group, you have like the degree, what called shift corresponding minus sign. Right? You have something like this. And there's minus sign here, so it doesn't matter whether you put here or here. So it's min and max, so it's precisely correspond to that. So notice that there's exactly one-to-one correspondence between the K group and this logical ring. Okay, so this is a nice thing. And you can relax the condition. The condition I put here, because it's a polynomial, because I said that everything is infinite generator, so it's a polynomial. If you do not have polynomial, you have if you do not put condition that everything is finite index, you have infinite many degrees. That is what it corresponding to the Novikov series, which is also appears very often in symplectic geometry. And we have this correspondence K group with this Novikov series. Okay, so I think probably I should stop here. Right, the time is up. Right.
Are you stopping now, or do you want to take a few more minutes?
I'm asking, should I stop now? I have another few minutes.
Yeah, you can take 5 more minutes if you want.
Okay. Okay. Now, once you have this K group, right? There's something nice on the K group. I think in the classic story, there's something called Euler pairing in the K group. So you can compute two things, pair them together in some way. But here in the TPC, you can also do this pairing. Here's a theorem that under certain condition, I'm not specifying what condition is. There's a well-defined pairing, which is not necessarily symmetric from the K group of a TPC to a K group of TPC, and from tensor product of a K group to the lambda p. You will be very curious at where does lambda p comes from. And here is the receipt how you do this pairing. You take two things, two objects. You can take two objects in class as a class, or you can take two objects as an object. Take two objects. You consider morphism set between the x and the shift of y, or the translation of y. And notice that this is a persistent module by definition of TPC. And the persistent module can be transferred to a filter chain complex. And once you have a filter chain complex, there's a map here, but I do not specify what this map is. You will go from this filter chain complex directly into the K group. And the transition, the precise transition we did here, that you transfer from the filter chain complex to a polynomial in this way. So again, you see two objects, consider the morphism set with translation of y. You transfer to a filter chain complex, you pass to an object in the Novikov polynomial, and you sum things up by this alternating sum. It depends on which transition that you have. And this is how we define pairing. I think it's probably, to some extent, it's very similar to the classic Euler pair. But here it's happened on filter version. So give two objects, you eventually get some polynomial. Yeah. And the difficult part is that everything I described here is an object. The difficult part is to prove that this is well defined on K group. And I'll take some time to prove that. Like here, again, let's take this very universal TPC, the homotopy category of filter chain complex. Now, what is this pairing looks like? It looks like perfectly fine. It looks like you have two things, T8 minus TB. Sorry, that's this. You have a E2 type. Let's take some example. Then you work out everything here, it will give you some polynomial like this. But it doesn't matter because you have a minus sign here, so it's actually plus. So it doesn't matter whether minimum is here or maximum is here. So eventually you'll get some polynomial like this. That's precisely what's the this will be the product of this polynomial with some negative of product of the next second polynomial. You'll get another polynomial. And if you work with a shift story, you will notice that this part is a classic one that we have seen earlier. This is home as an x0 functor. This part is x1 functor. It's a derived one. This is the first derived one. Actually, in persistent module, there does not exist any further ones. So see, something curious happens here. Right? So this also indicates some relation between the persistent module theory, or even the story, all the story here, the K theory with the shift theory, or even the derived story about shift. Okay, let's see the chat. Okay, okay, so let's see that. I have to see that this pairing. The reason why we define this is because this pairing can tell us something in the derived scalar category, because derived scalar category is a TPC. If you build in a filtered version, deal with Lagrangian submanifold in symplectic geometry, we can distinguish certain Lagrangian submanifold, while the classic machinery cannot do. This is the main application. And finally, I just say the following things. So once you have a K group, the advantage of all the things here, once you use entire information of TPC, is that you can associate certain pseudometric on the K group. So on the K group is really a quantitative K group. We can talk about what's the distance of two classes in the K group. And there's a various way to do that. And so sometimes it's related to a classic story. So sometimes you have to do something new called TPC autoequivalence. Okay, so I think that probably should stop. That's it.
Thank you, Jun, for the wonderful talk. Let us all unmute ourselves and give the speaker a big hand.
Thanks.
Okay, if you have any questions, please feel free to ask them now. You can either unmute yourself and ask the question directly, or you can put the questions in the chat. Right, Jin, can you see the chat?
Yeah. So I just read the quick question. There in this construction of persistent category lead in a natural way to define special invariant, defining earlier work of Shlukin. By the way, the name of Shlukin is spelling wrong. You see that this question is a little bit the construction of persistent category is something big, right? But the spectral invariant is something like associated to the object in persistent category. The spectral invariant can be okay. So if you have a persistent module, not persistent category, but persistent module, you can define spectral invariant basically just reading like the smallest left-hand side of the infinite length bar. That's the smallest left endpoint of the infinite length bar. So, so in this way, you can associate a spectral invariant for each class for each persistence module. But for persistence category, I'm not sure. Because persistent category is something big, right? So any quantity you read from persistent category is must be some relation between two persistence modules. You might be able to derive some numerical relation between spectral invariant of one persistent module to the spectral invariant of the other persistent module. But for each of the spectral invariant of each persistent module, it probably just go back to the classic story. There's nothing new there. Okay, so I'm not sure if I answered question one. So the question two is I forgot the exact definition of pseudometric unifier. does it interact with the other Hofer-like metrics, even the word metric on the group of Hamiltonian diffeomorphs? Okay, so the Hofer metric and the word metric is somehow related and somehow not. Sometimes the Hofer metric is fine, sometimes while the word metric is infinite. So some work related with that is Grothendieck. He constructs some example in 2 dimensions, okay, and the pseudo metric I defined here, which is I think you probably want to see this fragmentation. Yeah, the fragmentation pseudo metric. Yeah, so not by our work, by the work Biran and Cornea and Shrukin, they can set up everything more concretely, so you can direct compute compare with the Hofer metric. So in their story, I think the Hofer metric is somehow like the upper bound of the fragmentation metric. In this setup, we can actually breaklize the Hofer metric, and we can compare fragmentation metric with Hofer metric. But unfortunately, there's a catch. The catch is the number of the bar appears. So it's not a clean comparison. It's a comparison of the fragmentation metric, a pseudo metric, Hofer metric, and the number of the bars appears. So this is sort of making the estimation a little bit rough, because if the number of the bars become very large without increasing Hofer metric too much, then the estimation is very bad. So in this way, I think that the this algebraic fragmentation metric is somehow not very comparable with Hofer metric.
Thank you. Yeah, thank you for the question, Prakash, and yeah, thanks for the answers. Do we have any more questions from the speaker?
Yes, I would like to ask a question about the applications for derived categories of Fukaya categories. That you quoted briefly.
Yeah. Okay. So I can see it's not easy to see that. So we find some. Okay. So first, what is the object in the derived category? This is the infinite modules. And there's a conjecture that is basically proved. This has been proved. Every of these infinite module can be it's actually every infinity module can be represented by some immersed Lagrange. Immersed, not embedded. And then the natural question is, if I pass to the K group, I'm going to have a class of this infinity module. And the question is that possible to find some embedded Lagrange? After this is another embedding, you can represent this infinity or the class of this infinity module. This is basically you fight with immersed and embedded. But for the embedded ones, things are very nice. You can have a very well established Fourier theory for that. And we actually find some example that you will not be able to find. There exists some class that can only be represented by immersed Lagrange. And to do that, you have to find some criteria that what is the class that's represented by embedded Lagrange. And this criteria is actually given by this Perwhen. If there are some 2 modules, or let's say this, we have self-pair, we have x and x, we have a kxx. If this x is represented by some embedded Lagrange, then this pairing, after you compute this pairing, the answer of that must be, so here the answer must be nice in some numerical polynomial, right? But for that, if it's embedded, then it must be a constant. So this is a criteria, a necessary condition. You have to go through all the construction and then go through the definition of derived filters derived category. Now, so the question is, can you find some example which is when you compute this pair, this is not constant. We actually can find some example. This is actually not constant. It's very curious. And this example is not bad. This example will be like some of you can. The very first elementary one is some plumbing of 2 cotangent bundle of S1. And you have one circle, have another circle with some strange perturbation. But it's elementary. There's some other example that come from this Lipschitz fibration, which is probably take more time to explain. But I just give you some slightly more information how did the application works in this direct category. That's it. Is that good? Do I answer the question?
Yes, thank you. I would also like to know another thing. Do you know examples of derived categories which are TPC, or how can you
Derived
construct
category?
them? Yes.
Yeah, I wanted to ask something similar. Yeah. Thanks, Antonio.
Yeah. So here, I'm not sure if you know this. Okay, so if you try to do something like a derived category of derived category of persistent module is already TPC, because the persistent module itself is basically like the so let me go in this one. This probably is better. It can include the one that you just said. There's something called topology category. If you are interested, you can search online. You get some feeling about that. The topology category is a derived category of shifts over the manifold M cross R. And here, to include the one that I just mentioned, you can think that M is a point. The manifold is a point. It's basically a derived category of shifts over R. Okay. And I claim this is a TPC.
Thank you.
Thank you, Antonio, for the questions. Yeah, thanks for the answers. Do we have any more questions for the speaker? If not, can I ask, Jun, can you go back to that flow chart that you showed at the beginning of the points or the topics that you wanted to touch? I just want to have a look. It's not a question, just, yeah, just a minute. TPC, KP, numerical invariant. Okay. Yeah, I just wanted to, because one of the questions talked about spectral invariance, and I remember the word invariant in this flow chart, and I couldn't remember if it was spectral invariance or something else. Okay.
The spectral invariant can be right. So as I mentioned, spectral invariance not really appears in the story here because it's a very specific
persistence modules. Yeah.
Object.
Yeah. Okay, if we do not have any more questions, let's thank Jun again for this wonderful talk and for making so many notes for this talk. Yeah, let's give him a big hand again.